Hello everyone, welcome to experiment number 4 of Mechanical Engineering Lab 2, Strength of Material Lab. The title for today will be Determination of the Modulus of Rigidity in a Circular Shaft Subjected to Torsion. This experiment is equivalent to the first experiment in which we determine the modulus of elasticity of normal rectangular plates or specimens. So the difference will be that instead of modulus of elasticity, we are studying today modulus of rigidity, and that's why we have the circular shaft instead of rectangular blades and torsion instead of tension. So the value of shearing strain or angular strain gamma, it's a ratio between the shear force the shear stress tau and the modulus of rigidity. Very simple. So for now we need to find the value of G, which is the modulus of rigidity. Good. So the first element of this equation is the shear stress itself, tau. Tau as the shear stress is coming from the bending moment and radius of the shaft and the second moment of inertia. If I look at this figure, this is the value of angle theta, and we will have an angular strain gamma. This value depends on the radius. So if you have small radius, you will have less value of shear stress. If you have higher radius, you will have higher value of shear stress. And that's why for our calculations you can see that we will take or consider the maximum shear stress, in which the value of radius will be higher, which is d over 2. If you go back, yes, so bending moment, radius, and second moment of inertia. For a hollow shaft, it's pi over 32, the outer diameter square to the power 4 minus inner diameter to the power 4. So this will be the maximum shear stress, so the critical moment, second moment of inertia, and radius. And we know that now the strain, the angular strain or shear strain, is the maximum shear stress, the maximum one, divided by modulus of rigidity. So if you want to make the equation simpler, instead of writing the moment or diameter or I, so this is the final equation, the modulus of rigidity, which is already, we know that it's the shear stress divided by the shear strain. It will be calculated from 8 multiplied by P, which is P is the force, A is a distance in which you are applying the moment, and D is the diameter, outer diameter, by D small, D capital, and epsilon. So our test piece, our test piece, specimen number 3, is the shaft, hollow shaft, and then we have this arm in which we will hang our loads. So this will be the distance A. We have 3 sensors, sensor number 1, 2, and 3. We will measure elongations or deformations in the axis, the middle, and then shift it 45 degrees for S1 and other 45 degrees for sensor number 2. This table shows the properties or dimensions of the specimen: inner diameter, outer diameter, and length between the running end of the shaft and the strain sensor. So equations for theoretical calculations. Equations, as we mentioned, for strain from the experiment, we can find that the coefficient of sensor multiplied by the measurement, or delta 1, measurement from sensor 1. Then if you know the value of epsilon, you can put that value here and find G by using the same equation, and that's it. So you have the values of strain from experiment, and then you can find the value of G, which is modulus of rigidity. Preparation and conducting the experiment. If you want to assemble the test machine, we will follow the steps. Step number 1, install specimen number 3, the same specimen, in the fixed support number 5. And then step number 2, attach the spin bearing assembly, this bearing, because we need to support this shaft. So this is the bearing. Step number 3, we need to make sure that this shaft is leveled, 0 angle, there is no rotation or deflections. So we have this device to make it horizontal. Step number 4, we need to mount the pole number 6 element. So this is the support, and we can rotate this screw to raise the height until it's fixed with the bearing. Step number 5, we need to attach the magnet level to the central part of the specimen. So you remember, in this step we made the arm leveled 0 angle so that we don't have any initial angle, and now we will make it to the other surface of the shaft so that we don't have any deflection initially. After that, we can raise or control the upper half of the pole so we have that level horizontal. And lastly, you will add our weight to be fixed in this element in here. Remove the level and hang the setup for force application. This is force application in which we will apply some forces because of the gravity. It will make some load, and then finally attach the connectors on specimen number 3. So this is for the force, and there is one connectors in here to read the sensor number 1, 2, 3, and send the data to the computer. Okay, let's go and conduct our experiment. Good, so let us assemble the experiment. Step number 1, we need to install the specimen number 3. This is specimen number 3. Install it into fixed support number 5. So this is fixed support number 5. I can take the specimen and fix it to fixed support number 5. Good. I am not fixing this yet because I have more components, so at the end I will try to fix that component to have a specific level. Step number 2, we need to attach the spin bearing assembly number 8. So this is the bearing assembly number 8. I need to attach this into our specimen to have some support. Step number 3, we need to hold the level at the lever section of the specimen and adjust it to horizontal position. So this is our step number right now. So I need to have this level horizontal. So if you look at this point, it changed when I change the level. Yes, this bubble. Good. So right now the level is horizontal, so I can fix my component, and that's perfect. This is good. Step number 4, we need to mount the pole number 6 into the mounting hole number 5. So this is pole number 6, and this is hole 1, 2, 3, 4, 5. So I need to fix that at hole number 5. This will work as a support for the whole experimental whole system. And then after that, attach the magnet level to the central part of specimen number 3. So now the first level was in this plane. Now the other level will be in the other plane, which is very good now, but imagine that if I apply some load, you see the point is changing now, or other side. So I need to fix it to have a horizontal leveling by rotating this. And I need to make sure that this is horizontal. Yes, this is perfect. Good. And last step, I need to attach this item for loads, for hanging loads. So this will be our measurement tool to apply the external load. Example, this is 1 kg. I will put this one in here. So because of this load, because of gravity effect and weight effect, I will have some deflection. This will be the arm, and I will have some moment for the shaft. Each time in the experiment I will apply one more load, and then I will see that what is the deformation because of that load. This sensor, the weight will be recorded to the computer through this item number 1, and also the readings for strain will be recorded to the computer through this sensor. So this will be the second connection, sorry. Yes, now we are ready to do the experiment, so let's do it. Good. So for conducting the experiment, we already assembled our test machine as described above. So now we need to run the strength of material lab software by double clicking the respective icon on the desktop. If I go to desktop, strength of materials, double click. So experiment number 4, this is determination of the modulus of rigidity in a circular shaft subjected to torsion. Double click on this experiment. So we have 3 tabs. The first tab is for the specimen parameters, coefficient of sensors, inner diameter, outer diameter, distance between the running end of the shaft and the strain sensor, and reach of the arm, modulus of shear, everything. Second tab is for the table of increments and stresses. So when we measure the sensors value, it will give us reading number 1, 2, 3, 4, 5, and lastly our results and diagrams. So after the at the end, when we finish everything, we will see the graphs of readings from sensor 1, 2, and 3. Good. So if I go back to the manual, let's see step number 1. After we open the experiment, we need to start the software. So start. Now we are ready for performing the experiment. Apply 0.5 kg force or 0.5 kilogram weight, and then click measure. So I will be adding 1 kilogram force weight and measure another kilogram, another 0.5 kg. So the total weight is 1, measure, and as I add loads there will be some moment applied to the arm so that we can measure the values of strains and stresses. A third 0.5 kg, total is 1.5, and another 0.5 kg, so that total is 0.5, which is 2 kg, 2 kilograms, and measure. So this is the end of the experiment. If I go to diagrams, I will find that for sensor number 2 there is no deflection. For sensor number 1 we have a negative stress, negative deformation, and for this third one, sensor number 3, I have another positive stress or deformation. Good. If I want to save these results, I will go to menu, save. Automatically an Excel file will be generated in my computer. Disk C, strength of material, Excel file. Yes, this will be our file for the experiment. If I open the file, I will see the specifications of the specimen, all readings, and one table for calculations for experimental and theoretical, and other table for conclusions and deviations. And this is the end of our experiment. Thank you very much.